All right. Well, happy Monday. Thank you for coming back for the course. Really appreciate you guys still remember the course. As a joke. Uh, I heard several messages through the weekend asking about the homework and specifically about homework number 8. I think the homework number 8 is supposed to be turned in today, Monday, if I'm not remember wrong. So let's just take a look at it and see if we need extension on that. All right. First of all, let me share the screen. So you'll see the homework. Here we go. And this should be it. Okay. So can you guys see it?
Yeah.
All right. Okay. So this is the one-way slab figure that's showing the homework. Now, first of all, there are two directions, right? We have this vertical direction, or you can call it longitudinal direction, and there's labeled as 1, 2, 3, 4, etc., etc. And there's a transfer direction, which is A, B, C, D, right? So you want to determine which one is the one-way slab direction first. So we said the shortest span, the shorter one of the two, will be the one-way slab direction, right? So that first tells us that it has to be in the direction of 1, 2, 3, 4. Okay, so that's the first thing. And in addition, the problem tell you that it's a one-way slab unit strip like so, one-way slab unit strip like so. Okay, so this is what we have. This is what we have. I'm not going to go in detail, like specific how to solve the problem, but I probably want to talk about in a general, what is the approach? What is the approach here? Okay, so let me stop sharing here and share my screen so I can draw some drawings for you. Okay, where are we here? Okay. 1 second. Okay, so just trying to copy the drawing you just seen from the problem. So you have this direction, you have this direction. Naturally, in this direction, I have a shorter span. I have a shorter span. So this is what we got. Okay, and each column sitting on the corner. So this is a column, and I have a skipped one, and this another column. Skipped one, this another column. Skipped one, this is another column. This is what we have. This is what we have, right? So correspondingly, I have 3 bays. So 1, 2, 3 additional column groups, and this is that, this is that, this is that one, and this is the others here. Okay, these are all the columns. These are all the columns. Okay, and now I connect them with my beams underneath it. I connect them with my beams underneath it. Okay, so we said, given that the direction is L1, this is the one-way slab direction, and tells you already this is a one-way slab strip, shows you the strip right here. Okay, so pretty much you already know what you're designing for. Okay, what you're designing for. So the reinforcement, if I want to use blue here, the reinforcement is going along this direction. Flexural reinforcement going along this direction. Now, the real problem is which section is the section we're looking at when we talk about moment coefficients. Okay, so that's the real question. So I'm just gonna go ahead, cut the different grade. All right, so naming this one is A, naming this one is B, this one is C, this one is D. Okay, I have A, B, C, D, 4 grade. So I'm just gonna go ahead, make assumption. I'm gonna cut here, C. Okay, and you notice that this is where my eye is seeing. Okay, this is where my eye is seeing. So when I cut it, okay, and let me just make sure I have this consistent. This is 1, this is 2, this is 3, this is 4. That's what I have, right? So when I cut it, I expose the cross section, So this bay C, okay, C bay will looks like this. Okay, so 1, 2, 3, 4. So I have this, I have this, I have this, and I have this. That's the 3 main, right? But be careful now. I have also this one, this one, this one, because these are also beams. These are also girders underneath it, right? So don't forget, I also have this one, this one, this one. Okay, so Let me redraw it. Essentially, you have more. You have more, okay? Yeah, hold on a second. You have more, right? So if I redraw it, I end up with a lot of spans, So 1, 2, 3, 4, 5, 6, 7, 7 of them, right? So I have 5 in the middle. So this, 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 then this. Quite busy, okay? So this is actually what you're looking at, okay? So this is grade C, all right? So let's see, right? This is 1, okay? And this is 1 prime in the problem, right? And this is 2, okay? And this is 2 prime in the problem. And this is, I believe, 3. Oh, sorry, it's already given. Let me do this, okay? And this is 3 prime in the problem, right? So 3, 3 prime, and 4. And that's the span, All right, so this is where we're gonna determine the moment coefficient. So the span distance is Ln, so this is clear span length here, 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 right? And corresponding to here, 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 here. Okay, so when the homework is asking you how or whether you can treat it and apply the moment coefficient from ACI, this is where you're going to use the span length. These are the distance you use for span length. Okay, so this is the first question, right? Which is the direction of span? Okay, this is what you used to design. This is what you use for design. Okay, all right, so this is the first question. Second question, the distributed load, right? Say, when we have this, we said, okay, we're gonna simplify this. Remember, simplify this into reaction, 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 and we say, let me use different color, and we have this omega u on top of it, all this omega u on top of it, right? Omega u on top of it. So the question is, what is this omega u? Okay, so naturally omega u has 2 factors or 2 parts, 1.2 dead plus 1.6 live. We all know that. Now in the problem, in the example problem I talked about in lecture, I already give you the dead and live load. You just need to plug in and you calculate. Now in this problem, you need to calculate it. Matter of fact, if you pay attention to your homework, right? On the right bottom corner here, there's a label that says 5-inch slab, 5-inch thick slab, and live load is 50 PSF, pound per square feet. That's labeled there, 5-inch thick slab and live load of 50 pound per square foot. Okay, so we have to convert these numbers into omega dead load and omega live load. How to do that? So first, before you do calculation, I want you to visualize where is this strip of slab you're looking at. What is the load that you're looking at? The load sitting on top of it is basically 1 foot of strip. Let me use a blue color here, okay? 1 strip with a width of a foot sitting on top of it. There's a Whitman above. It's just a giant slab. Why you just pick 1 foot? Because when we design it, we only take 1 foot per design, and the reinforcement take care of this foot. So when we have all this design, the spacing between reinforcement is going to take care of every individual strips, right? Every individual strips. So when you design it, you only need to design 1 foot of strip sitting on top of these. Okay, so that is known. If that is known, let's calculate, right? So for the dead load, how do I calculate the dead load, right? So the dead load equal to the weight of the 1 foot of strip sitting on top of it. 1 foot of strip sitting on top of it. Okay, so be careful now. The cross section looks different. Okay, why? Because now this is what the red looks like when I talk about the span direction. When I calculate my dead load, let me use different color, okay? When I calculate, I have to take a different cut. This is the cut, you see? This is cut. So if I do this cut, this purple-ish cut, what I see is, if I do this, what I see is this is the column underneath it, and this is 1 foot, and this is the height HF, and that is the shaded area is the self-weight of concrete slab sitting on top of my beams or girders or whatnot. Okay, so in this, the dead load calculation becomes the height of the slab, okay, divided by 12-inch per foot, because this is per foot, okay, and multiplied by the weight of concrete, 150 pounds per cubic foot. Pounds per cubic foot. Okay, so this is how you calculate the dead load. How you calculate the dead load. Nothing else. Nothing else. Okay. Okay, so this is how you calculate dead load from the slab. Now the live load tells you already is 50 pounds per square foot. So you just use that. You just use that. All right. Okay, so that's the 2 critical questions I believe that we need to know the answer to, right? The first question is which span length or which span direction we're talking about. That's the span direction we're talking about. Second question is how to calculate the load. How to calculate load. Okay, I believe the rest of the problem can be solved. Rest of the problem can be solved this way. Okay, but give a try. And if you have any question right now, can you hold a little bit because we're going to go back to the course and stay behind. Okay, once we finish this course, stay behind and we can discuss in more details. Okay, all right. Okay, so quick call. Any big questions? Did I miss anything big in terms of big picture wise? Did I miss anything? Guys, any questions so far? Quickly. Anything? All right, okay. So if you want to reserve the question after the till after class, this is fine, okay? So just stay with me after class, have a more detailed question to calculate this, okay? But this is the general scenario for this homework. This is the general scenario for this one-way slab. All right, now I think you probably haven't finished one-way slab by yesterday's record. So I'm gonna go ahead and extend the one-way slab homework due the same time on Thursday this week. I'll give you a little bit more time. As I said, the homework number 9 is simple, and I can talk about today how we're going to solve it. So I don't think it's a lot of work. So Thursday with this homework plus homework 9 should be okay. All right. But anyhow, I'm going to walk you through how to solve homework number 9 today as well. Okay. Which is finishing the rest part of the serviceability on the moment of inertia. All right. Okay. So let's get back to the issue at hand. Okay. So this is more like homework. All right. So the real issue at hand today is to continue. So today's lecture 21, okay? Continuous serviceability, right? Serviceability. And specifically moment of inertia, okay? Moment of inertia, specifically moment of inertia. All right, so this is where we're gonna continue, okay? So let's take a look, all right? So recall what we have learned last time. Remember, I have to drag all these curves again, drag out all these curves again. So this is moment, remember, this is moment, this is curvature, okay? And we have 2-stage behavior, actually 3-stage, linear, and then this way, and then yielded. Okay, so let's cut it out into 1, 2, 3, and we say we only care about stage 1 and 2 for serviceability, because stage 3 is strength, is ultimate strength. Okay, so in terms of 1 and 2, right? We also give them names. Stage 1 is uncracked. Stage 1 is uncracked, and stage 2 is cracked elastic. Cracked elastic. That's the 2 sections we talked about. Okay, and specifically for uncracked section, okay, what we're looking at a beam, that has a reinforcement here, AS, okay, and then we have to transform it, right? Transform into a shaded area, shaded concrete section, right? This is the concrete section. Fill it in, fill it up, right? And then with a strip sticking out that converted from steel. So this is N-1 AS. And N defines as a ratio between Young's modulus of steel and Young's mass is concrete, and approximately equal to A. Approximately equal to A. Okay, so this is for uncracked section where we calculate the moment of inertia, calculate the moment inertia, and then we talk about cracked elastic. Excuse me, cracked elastic. Okay, for now we know once I have crack across the section, I have crack across the section, the top part is in compression and the bottom concrete just gone. All right, and then the neutral axis sits somewhere here, and steel is sitting on the bottom. And after transformation, what I'm looking at is top, I have a compression block. I have a concrete compression block, and the bottom here, I have a reinforcement strip like this, okay? And then this is what the cross section looks like. And we also mentioned last time, the compression zone is called KD, okay? D being the depth of the rebar, okay? And we went ahead, did some calculation to prove, right? And you realize that K equal to square root of 2 rho n plus rho n squared, okay, minus rho n, okay? And rho being the definition of the reinforcement ratio is area of steel divided by width and depth of the cross section. And the converted steel, the strip here, equal to N times AS. Okay, so that's it. That's all we have talked about, the cross section of uncracked section and the cracked elastic for these two stages. Okay, but there's something else we did not elaborate, right? That's the stress. Right? So stresses. So if I say this is transformed section, okay, and I'm going to talk about stresses. What are the stresses? So for uncracked section, no crack developed. Okay, so I'm going to draw the drawing. So this is the section. Okay, this is the section. And remember, there's little wings. Okay, these are little wings, right? So I want us to calculate the stress. Right? So first I need to identify location of stress. Okay, so the compression, here, oh, too big. The compression is somewhere here. Okay, somewhere here. This is the compression, right? And to be more specific, let me just use a dot here. And this is FCC compression. Okay? Different colors so see better. FCC. Okay, and also at the bottom here, compression, right? Sorry, tension. Okay, this is in the concrete. Okay, so that's why I use the same color right here. Okay, the bottom here, this is tension for concrete. Okay, and since it hasn't cracked, so I'm gonna set as FCT. Okay, FCT, which is tension concrete. Okay, and don't forget we also have the tension in steel. Okay, tension in steel. Right? So we call this Fs. That is the tension in steel. Okay. To compute the stress, we need a moment inertia. Okay. We also need a location. Okay. And we already have them, right? These are the location of the stress. So first thing, concrete compressive stress. Okay. So FCC, this fellow here, equal to moment. Okay. Y top. All right, that's the distance between the top fiber to the centroid of the section. Okay, Y top, somewhere here, and then divided by transform section, right? Moment of inertia of transform section, IGT. Okay, and concrete tensile stress, okay, which is FCT, that equal to the moment. Okay, multiply distance, which is H. Be careful, this is the height of the section. Okay, H minus the Y top. Okay, and let me lay it out. This is H minus Y top. Okay, divided by the transformed moment inertia, IGT. All right, now these are no surprise. These are for concrete. And remember, we converted steel to concrete. So we can directly calculate the stress in concrete. However, the steel is a little bit tricky. Okay, steel is a little bit tricky. Okay, steel tensile stress. Why so? Right? Why so? Because it's a composite section. Remember, so the stress in steel Fs equal to N, which is the modulus ratio multiplied by moment, modular ratio multiplied by moment, then D. Okay, depth minus 1 top minus y top, then bracket outside and divided by IGT. IGT. Okay, so that is the tensile stress in steel, and just the key factor here, this is the modulus ratio, and don't forget to multiply it. Don't forget to multiply it. Okay, and this is depth here, not age, not age. All right, so this is stress for the uncracked section. Okay, forgot to label 1. Uncracked section. Okay, for the cracked elastic, things a little bit different. Okay, a little bit different. So cracked elastic, let's take a look. Okay, once it's cracked, we say the concrete and the tension side completely lost its function. Okay, completely lost its function. There's no tensile resistance concrete, remember? There's no tensile resistance of concrete. Okay, so what we have, right? What we have here is this, which is going to have this section. Okay, and we have a compression zone. Okay, and remember, this is KD. Okay, and we have a tension of steel here. Okay, so this is Fs, tension of steel here. Okay, all right. So now the neutral axis is sitting right here. Neutral axis is sitting right here. Okay, and now if I want to find out the compressive stress is still here in the top fiber, FCC. Okay, and the tensile stress naturally is just right here. So this is Fs. These are the two stress we only care about. These are two stress we only care about. Okay, now the equation is a little bit tricky. The equation is a little bit tricky. Okay, so considering this is KD, okay, and you have to calculate that to find the neutral axis. Remember, and KD, we had equation for it. Is this plot, right? So we already have equation here. So you don't use the regular equation. Instead, right, FCC, compressive stress in the concrete, equal to 2m bending moment, okay, divided by JD, okay, and explain what JD is. And this is K, okay, D, and multiplied by B. All right, and the tensile stress of steel Fs in the cracked elastic stage is moment divided by As, area of steel, divided by JD, and JD equal to D, which is the depth, multiplied by 1 minus K divided by 3. Okay, 1 minus K divided by 3. All right, K is the ratio right here. K is the ratio, okay, of compressive zone, right? Compressive zone. Okay. All right, so you see, this is how we calculate the stress for both sections, how we calculate stress in both sections. But the elephant in the room, is that we haven't shown you how to calculate the moment inertia, right? We haven't shown you how to calculate moment inertia. I mean, of course, last lecture we showed you how to use symbols and equations, but we didn't show you an example, right? How to calculate this IGT. Okay, and in this case, how to calculate this KD in numbers, right? And JD and whatnot, right? So today we're going to show you an example. Today we're going to show you an example how we do this, All right, okay, so today let's show you an example, okay? Example. So example, okay, determine the IGT, transformed section moment inertia, okay, and stresses. Okay, for a section, okay, under a bending moment, bending moment of 45 kip feet. Oh, sorry, 45 kip feet. Okay, and giving you some parameters, compressive strength of concrete for KSI, and naturally, just want to put the modulus rupture here. Remember, 7.5 multiply square root of prime C, and this is 475 psi. Okay, How to use it, I'll show you, okay? And then the yield strength of steel, Fy equal to 60 KSI, 60 KSI. Okay, all these are material parameters, okay? Now the section looks like this, a pretty nice rectangular section. Have a width of 10 inches. That's the width. Okay, and I have three number 8 bars. Okay, a little bit odd, three number 8 bars. Okay, and the height of it is 25 inch. Okay, depth of the bars is 23 with a concrete cover of 2 inches. Pretty straightforward section. Okay, all right. So how to solve it? How to solve it? All right. So first thing first, I know I'm gonna have 2 stages. So first, I want to take a look at uncracked. Okay, first I want to take a look at uncracked. I mean, it's just different colors, so you can differentiate this solution one. Okay, sorry. So solve uncracked. Okay, this is first uncracked. So to get uncracked, I need to transform. So I'm going to draw out the section of the transformation. This is the major block from the rectangular section, and I have these little wings. All right, and I'm going to start naming the terms, right? Naming the terms. First of all, I have a white top. That is the center of this whole section. Apparently, this is a bit too low. Okay, apparently, it's a bit too low. So let me draw a little bit lower a little bit. Right here sounds more reasonable. So this is the center of the whole section. Center of the whole section. Okay, and now I have 2 parts, which is the middle part, which is rectangular section. I have these little wings. Call it 2. So 2 components. Okay, so immediately I know that all these area, right? Area, this is n minus 1 as, and this is bd. So this is a1, this is a2. I know the area immediately. Okay, not only that, I also know the height. I also know the centroid. Right? So this is the trick. I already draw the transform section. Next step is to find the moment of inertia. Okay, before I find the moment of inertia, I need to find a white top, which is the center of the section, which means I have to sum the area multiplied distance, which is called the static moment, divided by the total area. So I need a reference line. Okay, I got to start from somewhere, and I call this top line here a reference line. Okay, reference line, and you understand why we use it. Okay, so this is reference line. So now I have a distance of the centroid of section, black dot here, to this reference line called white top. Okay, I also have center of the first piece, right? A1. Okay, I know it's gonna look at top here, and this is called Y1. Okay, Y1, and now here at the little wings, right? Little wings, the distance right here is called D or Y2. Okay, D or Y2. Right? So this is the geometry I have. Now, before moving forward again, I have to recall a critical parameter that is called modulus ratio n, that is equal to ES over EC, which is modulus ratio n. Recall for steel, Young's modulus is 29,000 KSI. 29,000 KSI, right? So 29,000, there's 3, right? This is converting back to PSI, right? PSI, okay? So this is 29,000, okay? PSI, right? 29,000. No, sorry, 29 million PSI, right? That makes sense, okay? And the concrete is 5,7, right? And multiplied by square root of 4,000 PSI concrete. Okay, and I have this ratio approximately equal to 8.0. Okay, so with this, immediately n minus 1 as, which is the area of part 2, equal to 7 multiplied by 3 multiplied by 3 bars, right? And multiplied by a single bar of number 8, so as for number 8, and this is about 0.79 inch squared. So I have the total steel of what? 16.59 inch square, and this is after conversion to concrete. Okay. All right. Okay. So this is the basic number I have. And you notice when I start solving the problem, I say uncracked. Is it really uncracked? Is the section really uncracked? Do I know that? Do I know the section is uncracked or not? Okay, or did I make a right assumption here? Right? I don't know. I don't know. I don't know the crack isn't. I mean, I don't know the section is cracked or not. Why? Because I haven't checked the stress in my section yet. And why I haven't checked the stress in my section yet? Because I don't even know what's moment of inertia. So I start off by assuming it's on crack, calculate the moment inertia, then calculate the stress and compare the stress with cracking stress to see if my assumption at the beginning is right or wrong. All right, so that's the logic here. That's the logic here, okay? So just say assume uncracked. Okay, so I'm still working under the assumption that assume uncracked. So if it's uncracked, the top, y top equal to that equation, you remember sigma ai yi divided by sigma ai. In this case, a1, right? What is a1? A1 is b multiplied by d, so b is 10 inches, height is 25 inches, okay? And the distance between the center of it, this is height divided by 2, right? For the block, right? So this is 25 inches divided by 2 plus second area, we already calculate out 16.59 inch squared, and then multiply the depth, which is 23 inches. Okay, and divided by the total area, I have 25 multiplied by 10 multiplied by 25. Okay, just copy it down and plus 16.59 inch squared. Okay, so immediately I get my y top equal to 13.2 inches. So just mark down here, this is 13.2 inches. Pretty straightforward. Pretty straightforward. Okay, so now supposedly I have all geometries. I have all the geometries I need. Okay, I can then proceed to calculate the moment of inertia. I can then proceed to calculate moment of inertia. So how, right? So we're going to use that table. Okay, we're going to use that to calculate IGT. Okay, so first I'm going to set II, which is moment inertia of its own axis, moment inertia of its own axis, and area of each component, distance of each component. And be careful, this distance is centroid to neutral axis, okay? This is different. Centroid to neutral axis. Okay, and then this is AI, YI squared, right? Supposedly I add them all up, right? Add them all up, and I have it, Okay, so make the table, all right? And this is where I start, and this is part one. Which one is part one? This rectangular part is part one, right? This rectangular part is part one, remember? Okay, and then the area, right? Area part one is known, right? Okay, area, let me finish this table here. Okay, this is 10 multiplied by 25. Okay, and the moment inertia for its own, right? So it's 1 over 12. B is 10 inches. H cube, right? 25 inch cube. Okay, 25 inch cube. Okay, and then I can get this number to be 13.021 inch 4, the power 4. Okay, and this is 250 inch squared, 250 inches squared. Now, centroid of part one to neutral axis, centroid of part one to neutral axis. What is that, right? Y1 bar, right? What is Y1 bar? So let's take a look. Centroid of part one is right here to the neutral axis to the y top. So this is the distance of Y1 bar. This distance is Y1 bar. So I want to calculate this. So this is Y top minus H divided by 2. Okay, so turns out this is 13.2 inch minus 25 divided by 2, so 12.5 inch. I have 0.7 inch, pretty close. 0.7 inches. Okay, now AI, yi squared, so this fellow multiplied this fellow square, so 250 multiply 0.7 squared. I have this number to be 122.5 inch cube. Wait, sorry, no, cube 4. Okay, power 4. Okay. All right, so that's the first component. That's the first component. Not bad, eh? Not bad. Okay, so carry on. I'm just gonna use the natural divide line here. Okay, carry on part 2. What is part 2, right? Part 2 is this little wing fellow here, right? N-1 AS fellow right here, okay? That's the part 2. First thing first, I need to find the moment inertia with its own axis. We talked about this last time, right? This is its own neutral axis right here in the center of the bar. And I have to use 1/12 BH cubed. Now the problem is this H for this fellow here is very small, very small. So almost negligible, almost negligible. So I'm gonna say this is almost 0, approximately equal to 0. Okay, to simplify. And the area 16.59 inches squared. And you remember this N-1 AS. Okay, this is calculated previously. And the distance of its centroid to the neutral axis, right? Distance of its own centroid to the neutral axis. So it's D minus Y top. Okay, this is the distance, right? So this is Y2 bar equal to D minus Y top. Right? That's the distance between its own axis centroid to the neutral axis. So I have D minus Y bar top. Okay? So that is 23. D is 23, okay? Minus 13.2. And I have this number to be 9.8 inches. Okay, then subsequently I do the calculation. So this is basically 16.59 inch squared and multiplied by 9.8 inch squared, squared. Okay, and I have this to be 1593.3 inch to the power 4. Okay, inch to the power 4. Okay, now at this point I finish my table. And now I can sum them up. Right? And recall the moment of inertia of IGT equal to sigma of IO plus sigma of II bar squared. Okay, so recall this is the equation. Okay, I don't want to interfere in my table, so I'm just going to put it low here. You know what? Let me just put it up here maybe. Okay, remind us this is what it is. Okay, and then I'm just gonna perform this, add up, right? Add them up. I'm just gonna perform this adding up, right? So now this is sigma. So I add up together. This is I1 plus I2 at its own axis. This is 0. This is that. So equal to 13021 inch power 4. Okay. Now this not applicable. This not applicable. Here, last one. Okay, I have 122.5 inch 4 plus 1593.3 inch 4, and this gives me a 1715.8 inch 4. Okay, so I add this up together, right? Add them up together. What I got? I got total IGT equal to 13021 plus 1715.8. And you notice the unit matches inch to the power 4. And this is approximately equal to 14737 inch of power 4, give or take inch, give or take an inch of power 4. Okay. So that's his IGT for uncracked section. This is the IGT for uncracked section. Okay, so you see, we went through a little bit length to just find the moment inertia for this uncracked section. A little bit length just to find the moment inertia for this uncracked section. Okay, all right. So the moment has arrived that we are able to check whether our initial assumption that the section is uncracked holds or not. Whether the initial assumption holds or not, right? So let's do stress check. So check stresses. Okay, so now let's take a look at the compressive stress first, FCC. That is moment multiplied by Y top. and use the equation. Bottom here is IGT, okay? And you already forgot about it, but I still remember it's 45 kip-foot of moment converted back to 12,000 of pounds inch per foot kip, okay? That's a conversion. And then multiply by 13.2 inch, because that's the white top, divided by IGT, which is 14737 inch to the power 4, right? And now I got this stress to be 483.7 psi. So I want you to pay attention here. This stress is very low. It's very low, right? Recall the concrete compressive strength is about 4,000 psi. So this is about 1/10 of that. So this tells you that in a normal operation, the concrete section only takes about 1/10 of the capacity. Okay, so for example, when you sit at home, when you sit at, well, apparently not home, but when you sit at buildings, when you're looking at a column that underneath your seat, those columns or those beams are only taking care of 1/10 of the compressive strength. Okay, so we have a lot of reserved capacity for the concrete. Okay, but cut that short. The tensile stress though uses that equation, so moment multiplied by height minus y top bar divided by IGT, okay? And this is 45, again, 12,000, okay? And this is 25, which is height minus 13.2. I just saved the unit, okay? Because the same unit as previously. And this is 104, sorry, 14737, okay? And now I have this number to be crunched out as 432 PSI, 432 PSI. Okay, now moment of truth, moment of truth. I find this number to be smaller than the modulus of rupture I previously calculated, which is 475 psi. Okay, so uncorrect, assumption proved. Hooray, we're good. All right, we're good. So we don't have to worry about it. So it is uncorrect. It is uncorrect. With this moment applied to it, it is uncorrect. With the moment applied to it, it's incorrect. Now, with all this, right? Well, where I'm at it, I'm just going to calculate what is the stress in steel. Okay, so I'm using that equation. And don't forget modulus ratio must by moment and depth minus y top. These just the equation I'm copying down from earlier. Okay, and this is IGT. Okay, and bring the number in. 8 is the modulus ratio. Moment is 45. Okay, and don't forget the conversion factor, 12,000 multiplied by depth is 23 inches minus 13.2, and divided by IGT is 14737, and I got this number to be 2873 psi, 2 kips or 2 ksi. Okay, 2 ksi, and this is much smaller. I just want to put a note here, much smaller to the yield strength of steel, which is 60,000 psi. Okay, or 60 ksi. Okay, all right, so we're good. We're good. Okay, so this is for the uncracked section. This is for the uncracked section, right? So what we said is that we assume it is uncracked, and we went ahead and check, right? Realize that it is uncracked. Pretty happy about it. Pretty happy about it. Okay, all right. So let's say this is example number 1, part A. Okay, part A. Okay, and why I call it part A? Because I say let's apply moment 45 kips. And now let's introduce part B, which, right, which the moment will be increased to 90 kip feet, double it, okay? So I want you to recompute the stresses in the section, recompute the stress in the section, okay? So what to do, all right? So now let's take a look at B. Okay, let's take a look at the B, okay? So moment is doubled to 90 kips foot. Now from the first part, I already know it's uncracked when I have 45. Barely checked, right? Barely checked. So for 90 kip foot, I know for fact it is gonna crack. So assume cracked elastic. Okay, and this is stage 2. Assume it belongs to stage 2. Right? And then if that is the case, I just want to do a quick conversion here. and this is read number 8 bars, great, and I have 25-inch, fine, and width of 10 inches from previously, and 23-inch of depths. Practicing my quick draw here, and this is 2-inch of concrete cover, right? So now with this, I can convert the section. I can convert the section, right, into a compressed block. Compress the block top here, okay, and a tension bar here. Tension bar here. All right, and remember we said in a cracked elastic, this is KD. Cracked elastic is KD, and this is NAS. NAS. All right. Okay. Several things before we start. Okay. To do this, K, remember we had to use that equation. K equal to square root of 2 rho n plus bracket rho n squared minus rho n. Now we know n. N approximately calculated already equal to 8 from previous problem. Now we don't know rho, and rho is defined as AS divided by BD reinforcement ratio, and 8 bars, number 8 bar 0.79 inch squared, okay, and divided by BD, which is the section, so 10 multiplied by 23 inches. Be careful, this is BD, okay, not BH, okay. People sometimes make mistakes here, okay, and this is 0.0103. 0.0103. Okay, I want you to be careful, okay, on this B width here, because this B right now I have a rectangular section is that if I have a T section or I section, okay, this B is not the web, all right? This B is not the web. This is the flange. I mean, this is the gross, okay? Very big, okay? Large section, okay? So whenever you see I or T-beam section, it is always the widest distance, okay? Anyhow, I come back, right? So I have all these squared away, and then let's just calculate, right? So K equal to, bring the number in, rho, so 2 multiplied by 0.0103, and 8, which is n, plus bracket inside 0.0103 multiplied by 8 squared minus 0.0103 multiplied by 8. Okay, I got this number K to be 0.332. Okay, that means compressor zone is almost 1/3, 1/3 of the depths. 1/3 of the depths. Okay, so quickly, KD equal to 0.332 multiply the depth 23 inches, and I have that equal to 7.63 inches. Okay, and JD quickly equal to D multiply 1 minus K divided by 3. So bring the number in. This is 23 inches, and 1 minus 0.332 divided by 3 again. I have this to be 20.5 inch. Okay, so I got KD, I got JD. I'm pretty happy. Happy campers. Okay, so now I look at the section. Again. So the section looks very simple, right? Simplistic, right? So section looks just like that. Okay, compared to the uncracked, it's really easy. I have a KD, figured out. I have a steel, figured out. This is NAS. Don't forget there's no -1 here, okay? And I even got a distance between them figured out, which is JD. Remember here? So the center between the compressive zone to the bar JD, I got all these figured out. Okay, how to do moment of inertia. So I move out of the table again. I wheel out my old dear friend table. IO, so that is the inertial moment inertia, and AI, area, and YI, okay? And this AI, YI bar squared, and make the table just like that before, right? Just like I did before, okay? And I know this is 1 and this is 2, and let's call this 1 and call this 2. Okay, so for the first part, I know this is 112 and the width is B. Okay, so B and multiply KD to the cube. Okay, save the trouble, you can bring the number quickly. It's 370 inch to the 4. Okay, and AI, which is equal to B multiplied by KD, and bring the number in, you find that 76.3 inch squared. Now, YI is the distance between the centroid to the neutral axis. So the centroid is right here in the middle. So this distance KD divided by 2. very simple, right? KD divided by 2. So KD divided by 2, that gives me a 3.8 inches. Now AI y squared is easy, so just 1110 inch to the 4. Okay. All right. So for the little strip here, the moment inertia of itself, again, neglected, 0. Okay. Areas NAS, so equal to 18.96 inch squared. Okay. Don't forget there's no n minus 1, right? So this is a little bit higher than the uncracked section. Okay. Y bar is distance between the central to the neutral axis right here. So this is D minus KD. D minus KD. So D minus KD, it gives me a 15.37 inch distance. All right, and you just do AI yi squared, and you got this to be 4479 inch power 4, and that's it. That's it. Okay, so redraw these lines to flush it, and here, and here, and here, and here. Okay. All right. So to sum them up, I still need to sum them up, right? So I need to sum this one over here. So this is, and this is, shouldn't use this. You just use IGT. Okay. And since, okay, be careful, since this is cracked elastic, so I'm going to say this is ICR, crack elastic. Okay. So since it's a small table, right, I just need to add up. So I'm going to add up this fellow, this fellow, this fellow. So this equal to this, right? All these marks, right? You add them up together, you got a 5960 inch to the 4. Okay, that's the moment inertia. Okay, that's the moment inertia, ICR. Okay, ICR. All right, I have a few minutes, right? One, I'm probably over, but let me quickly do check stresses. Okay, check stresses. I just want to use the previous equation. I don't have to recompute anything, right? So if CC is 2M, use that equation, showed you earlier, JD, KB, D, okay? That is 2 multiplied by 90 kips. Don't forget the conversion, 12,000 divided by 20.5 inch, that is JD, K 0.332, 0.332, and multiplied by 10, multiplied by 23 inches. Okay, so eventually I got this to be 1382 psi. Now a little bit higher, you see, jumped up. And the stress in steel, Fs equal to M over AS JD. It's really easy. So 90 multiplied by 12,000. Don't forget the conversion. This is 3. This is 0.379 inch square 3 rebar. Okay, JD equal to 20.5 inch. I have this number to be 22.262 KSI. Okay, this is very big. This is very big. Okay, so now I'm done. Right? And note that this is much bigger than the rupture of modulus of rupture is 475 psi. Cool. So indeed correct. Okay, but this is lower than 60 KSI of Fy, so I'm okay. Now yielded, fine. Okay, all right, fellows, we're done today. Okay, so this is how you compute IGT, ICR, and find the stresses for them. Okay, I know I'm a little bit over, so just gonna start recording quickly. You're welcome to stay behind, have a question, homework, or else I'll see you on Wednesday, okay? Or else I'll see you on Wednesday. We have extension for this homework. I will post it online as well, okay? All right, guys. All right, okay. See you later and on Wednesday, okay? See you later on Wednesday.